next speaker is Simon Wilson from Trinity College Dublin, where he's in computer science and statistics. He's interested in applying Bayesian methods of statistical inference to a variety of applications in science, engineering, and the humanities, and in particular in reliability, telecommunication, astronomy, and ecology. And today, Simon is going to talk about sequential Bayesian parameter estimation in space-based model.
Okay, thank you. Just as I've listened to the talks in the meeting, I realize I may be somewhat of an outlier. My background is in a statistics department, which was merged some years ago with a bunch of computer scientists. I suddenly was exposed to wonderful and weird things such as graphical processing units and proper ways to write computer code and so on and so forth. My main interests are in Bayesian inference, and of course in Bayesian inference we certainly have lots of computation issues that are shared with machine learning. This talk is looking at estimation in state space models or hidden Markov models, and of course Bayesian inference has a nice Bayes' law is sequential in nature, which makes it a very appropriate way to do inference in a streaming setting or a sequential setting. So this is the sort of model that I'm interested in, because these models are in lots of places, and I've seen lots of applications. You have a latent observed process, which is Markovian, and you observe noisy realizations of that process. These are independent given the unobserved process X. So the model is specified by an observation distribution of y given x's, starting state for the unobserved process, and then the Markov bit, so how the unobserved process proceeds in time. And then if you're trying to do Bayesian learning on this model, you might want to prior on the parameters theta, which parameterize this model. Now, what are the usual tasks, inference tasks for such models? So I would contend that the first and the third one here are the most common. The parameters of the model are usually fixed to some appropriate value that's deemed appropriate, and you're interested in the filtering, so learning about the unobserved process given data, and you might also be interested in prediction. So what's either the observed or unobserved process going to do next, given data. Now, in this work, we want to do these tasks sequentially and quickly. So we assume we've solved these problems at time t minus 1. We observe a new data in yt, and we want to update our state of knowledge to that new time. And somewhat unusually for this field, we're actually going to concentrate on the estimation problem, the second problem here. What can we learn about these parameters in light of data, and how can we update our knowledge sequentially as data comes at us? As I said, most of the literature in this area will tend to just assume these parameters are known, or do some pre-processing that gets a reasonable value for them. Into that situation. Okay, there's two, again, simple manipulation of probability laws will give you two potentially useful results for these models. So the first is you can write the posterior distribution of theta given data up to a constant like this. Okay, just multiplication or probability a couple of times. And this is valid for any x where the denominator is non-zero. Here's another, perhaps slightly more useful updating equation. This allows you to go from time t minus 1 to time t by way of calculating this expression in weight. Okay. Again, at any value now of xt for which the denominator here is non-zero. And we'll also observe that for many hidden Markov models, many useful hidden Markov models, the dimension of theta is small enough so that you can actually just grid. You can define a discrete grid on values of theta so one can calculate this on a discrete grid. You don't have to resort to the Monte Carlo simulation. Okay. So that's where we're sort of starting off this work. So again, in terms of thinking about data streaming at a high rate, this is not very appealing. It requires us to work with distributions of dimension t. This one is more appealing. The new thing we have to evaluate at any time is of dimension 1, each of these expressions of dimension 1. So that's certainly more appealing. Updating equation, and also note that if we have solved the filtering and prediction problem, so it's these two distributions here, then we can evaluate this updating. So what that means is if we can solve the filtering and prediction problem, we can update sequentially our distribution on the parameters theta. Okay, the typical choice here for the x, we usually typically would pick x that maximizes this probability on the denominator for numerical stability reasons. But one can choose any x, shouldn't make any difference. All these formulae are up to constant proportionality, but again, assuming that theta is of low dimension, the normalizing constant is very easy to compute. It's just the sum over the thetas on the grid, discrete grid. To show you an example of a method that used the former rather than the latter updating equation, and that's not necessarily a good idea, I've taken here a very successful approximation for the parameters of a hidden Markov model, of any hidden model. This is something called the integrated nested Laplace approximation, and it uses this identity where an approximation to the filtering density, the Gaussian approximation, is done to the denominator term of the filtering density. And this turns out to be a very accurate and very fast approximation, particularly if the Markov process is itself Gaussian. So it turns out to be very accurate. Basically beats things like Monte Carlo, Markov chain Monte Carlo, in terms of both speed and accuracy very, very easily. Because we try to use this method for sequential updating, it turns out not to be a very good approach. Essentially the updating term we'd have to use at each time would be a ratio of Gaussian approximations of order of dimension t. So, okay, so it's not going to work very, very nicely as we get more and more data. We have tried, and we'll see later, we've tried to approximate this term further via the Gaussian term. We call this a crude approximation. So this would be now be quick, but as you see, not very good. Okay, things that do work for this are where you have some approximation to the filtering and prediction density. So this would typically be the case for lots of these methods. So things like Kalman filter-based methods would try and produce approximations to these terms. And of course, if we have those, then we can do our updating. So at time t minus 1, if we have some approximation to this distribution, we can produce an approximation at time t by using these two approximations here. Okay. So this is nice because now we can use any method that produces these approximations. We can use and see how it does. So we've tried lots of different approaches and tried them out on lots of different models to see how well they perform. So the simplest would be to use a Kalman filter to approximate these two densities. So of course that's exact if our model is linear and Gaussian. As soon as you step away from either of these, we're getting into approximate methods. So two that are very common are the extended Kalman filter, which the extended Kalman filter tries to cope with nonlinear models by essentially linearizing them and turning them into a Kalman filter. The uncentered Kalman filter tries to do something similar by trying to account for how the mean and variance of x change according to the nonlinear part of the model. So both are quite successful, and we can use those as approximation. And both of them, you get out a mean of the denominator term here, which you can use for x. Another issue with these sort of dynamically updating what you've learned about theta, in this case, is we have a grid of values over which we compute this, and of course that grid may change at time. So we've tried various methods for dynamically updating the grid. So one might imagine that as time goes on, what you've learned about theta may change, both in terms of scale and location. We tried lots of what we thought were quite sophisticated ways of updating the grid, and in the end, what actually seemed to work best was something very fast and simple, where we simply detected whether the existing grid was not big enough or too big by looking at what's happening at the edges of the grid. And then if we had to add new points externally, we simply did some linear interpolation. And if we had to add new points internally, again, we just resorted to some linear interpolation. The point here being that if you add new points to your grid, you don't have time to go back and recompute the entire approximation up to that point at the added point. You just have to, again, do some approximation. And again, we were quite pleasantly surprised that this is remarkably stable, even though it's an approximation to an approximation. So this is our algorithm for learning about theta. What we do initially is we use this integrated Nessler-Plus approximation to get our approximation to the posterior. And we do that because it's very accurate, and we do it for as long as we can. So we do it up to a point, to an observation t, yt, such that this is just becoming too slow a computation to do. Okay. And from then on, we do our sequential update, like this, where the filtering and prediction densities are coming from some, perhaps Kalman filter, perhaps other algorithm that's output. And then periodically, we check to see if the grid of values of theta over which we're computing this is either too big or too small or needs shifting in location, and we add, delete, etc. points and interpolate the values of new points appropriately. Okay, so a couple of examples. So the first is linear Gaussian. So if we can't get this right, then we might as well go home. Now remember this crude approximation using Inler, it works really badly. So, okay, we'll say nothing more about that. Of course, if we use the Kalman filter, we have an exact algorithm, so not surprisingly, it gets the right result. So the way to read these graphs is, here are the three parameters of the linear model. The black line is the true value, x-axis is observation time, red is posterior mode, and blue is a 95% marginal posterior interval. So of course, you see over time, we nail the true value of the parameters quite nicely, and the uncertainty is, of course, going down as we observe more data. If we compare this method to some other parameter estimation method like a particle filter, we can do some comparison in various ways. This is probably the best plot to look at. This is sort of the trade-off between accuracy of the approximation and computation time. So computation time is on the y-axis. This is log Mahalanobis distance between the computed posterior and the true value of the parameter. So you want to be down in the bottom left corner. That would be fast and accurate. Our method is considerably faster than a particle filter, which you'd expect because it's not doing Monte Carlo simulation. and it's sort of similar in terms of accuracy. So it's doing better than that. Okay. So here's a nonlinear model. Okay, so there's basically periodicity to the unobserved process, and the observations are roughly the square of the unobserved process. Again, there are 4 parameters in this model, and our method does quite well, except on one parameter, where it doesn't do very well at all. Although we couldn't actually get any other method we tried to work well. And again, if we look at the comparison of computing approximately posterior by, say, a particle filter, again, we just look at this graph. Our method here in red and black is generally actually more accurate and faster than a particle filter in this case. So it's better. And then finally, a non-Gaussian model. So here the observation equation is Poisson, so the y's are counts. And the unobserved process is just an autoregressive model. Now, to implement this for our method, we actually approximate the observation equation by a Gaussian. So, I mean, for x sufficient, if x is sufficiently large, you can approximate a Poisson by a Gaussian. And again, how does our method do? It does very well, again, even with this Gaussian approximation. We managed to nail the true value of the parameters very nicely. And then, again, over many runs, when we compare our technique to something like a particle filter, again, concentration on this graph, the red and the black are our methods, so they're faster than particle filters, but tend to be a little less accurate. So here there is that trade-off between computation time and accuracy. The nice thing about our method is that it doesn't slow down the time, so the method is not getting slower as you sort of the data. A couple of remarks. So first of all, the method is in some sense trivially parallelizable, at least over the grid of values of theta. Of course, calculations are done completely independently. It's easy then for us to average out over the posterior of theta to get marginal filtering and prediction, so taking account of the uncertainty in the parameters. This is, of course, a major restriction. So essentially the set of static parameters theta in the model must be small enough so you could grid it up. So anything beyond 6 or 7 parameters, your grid is starting to get quite small, perhaps in each. There's lots of work on corrections to things like UPF and ETF filtering and prediction approximations. So what we've tried is this very nice paper appeared a few years ago in JMLR. And these approximations work very nicely and really improve the accuracy of the approximation in many of the models that we've looked at. This is a nice question, sort of how you dynamically update this grid over which you're computing the posterior. So probably do a better job there of dynamically upgrading it. We've done something very crude. It appears to work for these rather straightforward low-dimensional models, but you could probably do something better there. Not that too much. So obviously these are all sort of things that one might now look to look at. Particular spatiotemporal data is an interesting one. There's lots of it, and of course it's less amenable to particularly parallelization because you're taking account of spatial correlation. That's the really important thing. So, so we certainly have lots of applications where we're interested in applying to this sort of data, and it's not so obvious that how we might do it. going beyond a set of, moving beyond a dimension of theta that you can simply grid up. There are various things one might do there which are useful. And then, of course, this whole idea of getting the grid, dynamically updating the grid. There's some work on this, but not very much. And that's something we'd also like to think about. Okay, so I'll stop there. Thank you very much.
Let's think Simon again.
And I've seen lots of applications. You have a latent observed process which is Markovian, and you observe noisy realizations of that process. These are independent given the unobserved process X. So the model is specified by an observation distribution of y's given x's. Starting state for the unobserved process, and then the Markov bit, so how the unobserved process proceeds in time. And then if you're trying to do Bayesian learning on this model, you might want to prior on the parameters theta, which parameterize this model. Now, what are the usual tasks? Inference tasks for such models. So I would contend that the first and the third one here are the most common. The parameters of the model are usually fixed to some appropriate value that's deemed appropriate, and you're interested in the filtering, so learning about the unobserved process, machine learning. This talk is looking at estimation in state space models or hidden Markov models, and of course, Bayesian inference has a nice Bayes' law is sequential in nature, which makes it a very appropriate way to do inference in a streaming setting or a sequential setting. So this is the sort of model that I'm interested in, because these models are in lots of places.
The next speaker is Simon Wilson from Trinity College Dublin, where he's in computer science and statistics. He's interested in applying Bayes methods of statistical inference to a variety of applications in science, engineering, and the humanities, and in particular reliability, telecommunication, astronomy, and ecology. And today, Simon is going to talk about sequential Bayesian parameter estimation in space-based model.
Okay, thank you. Just as I've listened to the talks in the meeting, I realize I may be somewhat of an outlier. My background is in a statistics department, which was merged some years ago with a bunch of computer scientists. I suddenly was exposed to wonderful and weird things such as graphical processing units and proper ways to write computer code and so on and so forth. My main interests are in Bayesian inference, and of course in Bayesian inference we certainly have lots of computation issues that are shared with